Assalamualaikum and good afternoon, student.
Good afternoon, doctor.
Good afternoon, doctor.
Are you able to see my screen?
Oh, the assignment.
Yes, doctor.
Can see, yeah?
Doctor, can I ask you a few questions regarding the assignment?
Alright, what about it?
Let's start from the problem 1, right? Just, problem 1, the second question. Because since we are using the GM plot, the Google map, we use the Google Distance Matrix API, right? So for problem 1, the question 3, question 4. So if you straight away use the Google Distance Matrix API, it will display the shortest distance already, which includes the route in the real traffic. So for question 4, it says that apply the algorithm. Then how do we apply it if we are using the Google Distance Matrix API?
Oh, because it's already the shortest path.
And that's one of the questions. And also for the problem 1, question 2, right? It says that the customers would like to make a door-to-door parcel, which means that a delivery hub, they will go to the customer house, and then the origin, and then go to a destination. And the questions say that get the distances between origin and destination. So in this case, should I calculate the distance only between the origin and the destination, or shall I include the distance from the delivery hub to the origin and then until the destinations, since the question stated it as a door-to-door parcel delivery? There's a second question.
Okay, so you have 2 questions.
And the third one also the same, because you also say that suggest the least distance. But since we are already using the Google Distance Matrix API, it's already shortest. And also if you use the GeoPy, right? The GeoPy, it wouldn't include the real life traffic like the highway or the road, right? It would just calculate the distance like between 2 points. So I don't think that's suitable.
Okay, anyone in this class having the same problem?
Yeah, doctor, same. And plus the origin and the destination coordinate, if you do the geocode function, right, you wouldn't get to find anything for Bukit Jelutong, and you get the wrong coordinates for Subang Jaya.
Sorry, it's not really clear. They were missing.
Oh, it's the geocode function. You get wrong coordinates of Subang Jaya, and you won't get any information from Bukit Jelutong.
Okay, alright.
Therefore, I hard-coded the functions into tuples of the location.
And also, if they ask us to compare 2 distance, right? The only 2 distance we have is the first one is from GeoPy, which is the displacement from 2 points, and the second one is from the Google API. And if we compare both of them, of course, the displacement will be shorter lah, as compared to Google API. So I think it's not applicable lah.
Desmond, would you like to add?
No, that's all from me.
Okay, so all of you feel the same way? Okay, think you feel the same way. Alright. Okay, I will revert on this later, because we need to I will revert in the written form.
And one more thing, doctor, may
Yeah.
I add one more thing? Because I saw the rubric, it says something like if it's hard-coded, you might get marks reduced. But in our case, if we use the geocoding toolbox, we can't really get like some of the coordinates. So is putting the manual coordinates provided in the question set or the question table in the form of tuples of the location considered hard code?
Oh, that one is not considered hard code. In the rubrics, what it means by hard coding is because student may do one problem done by one student and the next problem might done by another student, so they hard code because the output derived from problem one is because it is not integrated to resolve problem number two. So this is what it means by hard coding. But if you are just hard coding the coordinates, then it's okay. Okay, I will revert this because whatever that I mentioned, I need to make sure that Dr. Asmiza mentioned the same way too. Okay, because as you know that Dr. Raja and is having students from my lecture and also Dr. Asmiza lecture. So we need to say exactly the same thing so that this student will be okay. So we need to have consistent answer to this. Then we will try to answer it in a written form. Okay, since this coming Thursday is a public holiday. So any of the remaining question you can type at the chat session as this session begin. Okay, but thank you for highlighting this. For this, I'm answering question by Kishore. So there's no tutorial this Thursday. This Thursday is a public holiday. So the start of our session, before we begin with our lecture 8, I will need somebody to present your answer for advanced data structure part 1. Okay, and then throughout this lecture 8, we will be answering the remaining questions, but you still have some fractions of questions that you need to do, and you need to submit that, and you need to update that in our collaborative environment. So this applies to student T7, 8, 9 and 10. Okay, so let's say after we have gone through this, and I will look at your answer, and then we will see whether we need to do a replacement class to do the tutorial. Okay, if so, without further ado, I would like to have one representative from T7 to T10 to present your answer in tutorial 7. As spoken in the Telegram, I have marked your answer and all of them are correct. So who would like to present? Inamul Hassan, can you try? Would you like to try? Kishore, can you explain the answer?
Sure, doctor.
Okay.
Can you see my screen?
Yes.
Okay, so for the first question, we have to use the chaining. So we have to k modulus 7. 7 is the number of slots we have. And then once we have found the values, we can insert the numbers accordingly into the slots. But however, if there is a collision, we just chain the numbers, meaning we create a linked list for that particular slot. Okay, Doctor, do I have to explain one by one or just the concept?
Okay, student, any questions about how we get the 55653? Any question pertaining to this? Can somebody answer? Yes or no? Okay, choice here is okay. Alright, no question. So everybody is okay with chaining? Okay. Kishore, can you proceed?
Right. For the B, it is open addressing with linear probing. So we do the same thing, k modulus 7, and we get the values. So we see if there is a collision, we move to the next empty slot. We have to find the next available slot and then we put the number there. For an example, here 19 first, it goes to the 5, and then we have 26, which is also going to slot number 5. So there is a collision. So we see if there is any next slot, available slot. Yes, there is. Slot number 6 is available. So we put 26 there. So whenever there is a collision, we move to the next available slot for us to put the number. And then for C, quadratic probing. So whenever there is a collision, we have to use the formula hk equals to k plus I square modulus by 7, and we will get the value. And then we have to check whether is there any collision. Is there a collision? And if yes, we have to increment the I and then we calculate again until we get a slot which is free, and we put the number there. And lastly, open addressing with double hashing. We still use formula. Initially, we use the formula k modulus by m, and then whenever there is a collision, we start with I equals to 1, and then we use the formula given here, hk equals to 5 minus k modulus 5. And before this, the previous three methods, we have to put the number in the slot represented by this number. However, for this double hashing, instead of referring this number as a slot, we actually do jump. So for an example here, we already put 19 at slot number 5 and 26, we are getting 5. So there is a collision, we use the formula. We get 4. 4 here means, it doesn't mean slot number 4, but it means we have to jump 4 times from in slot 5. So first jump, second jump, third jump, fourth jump. So the number 26 will go to slot number 2. So that's how it works. Yeah, that's all.
Okay, class? Everything is okay? Double hashing is fine for you? Okay, if no, please let us know. Okay, let's move to question number 2. Kishore?
Question number 2. Which collision resolution strategy between these four is more appropriate when the load factor of the hash table is high? And the answer given in the collaborative environment is that chaining is the best strategy because chaining allows the load factor to exceed more than 1. Open addressing strategies such as linear probing, quadratic probing, and also double hash could only allow the load factor to be less than 1. Because the number of elements to be hashed and stored cannot be more than number of slots. That is why we use the best strategy is chaining.
Okay, so the best strategy is to use the chaining. Okay, so thank you so much, Kishore. If you have question, please let me know. So currently for tutorial 7, this is done by T7 and T8. Okay, T6 for, in case you are here, for your information, we are doing this, we combine our answer collaboratively, and I already marked, so this is my comment in green. Okay, so the answer is correct. But for T9, you have a typo, but okay.
Should I name?
This one is not 126, but it's 26. But I think it's just typo because when I look at here, is everything is okay.
Ya, betulnya ya.
Okay, so if you can see that for question number 3, question number 3 in tutorial 7 that we're supposed to do on this Thursday, we already have this in tutorial 5. Okay, because in tutorial 5 we already answered this question, which was question number 2. Okay. Alright, let's begin today's tutorial, today's lecture, which is lecture number 8, Advanced Data Structure Part 2. So last week we have learned about the types of table in data structure, which is the direct access table and the hash table. We learned a little bit about the hash functions and the 4 collision strategies, and you have completed your tutorial correctly, and as presented by Kishore just now, the answers are correct. Okay, so for part 2, we're gonna learn about the concept of binary search tree. So binary search tree was firstly introduced in tutorial 5. Okay, the reason behind is for you to do some active learning, because when you answer that question, you know that those answers were not in the lecture note. Okay, so but you answered it pretty well. But so today we're going to go in depth and with the formal definition of BST, and after that we're going to learn about the operation that can be done with the BST. So last week when we talk about part 1, we can see that we can do the searching at the order of constant value, okay, using the hash table and the direct access table. And we learned that even when we choose the right algorithm, we can able to reduce the space of memory. Okay, so we are not only reducing the time in completing the algorithm, but also to reduce the memory consumption. So for part 2, we will learn on how to exploit the BST in order to reduce the time complexity in traversal, searching, insertion, and deletion. Okay, because these are the most common operations that needs to be used in application. Okay, for most applications needs to use this. So this is the first time that we talk about the traversal. So traversal is a systematic way to visit all nodes in the BST. So this is the introduction for binary search tree. Search tree are data structure that support operations include search and to find the minimum, to find the maximum, the predecessor, the successor, and to do the insert towards the BST and to do deletion for the BST. So search tree can be used as both dictionary and the priority queue. So dictionaries are all these searchings, okay? It can have the same meanings as the dictionary in Python, okay, where we can derive the list, can do the insertion, can do the searching and all. And the priority queue is something like, for instance, right, we can find the priority can be the highest or the lowest. So for example, to apply minimum and or maximum as the priority queue, then we can say that okay, the highest priority is the maximum. So by finding the maximum, then we will able to identify what are the priority queue. So in this lecture, we are not going to learn on how we're going to apply this, but we are just going to learn about the concept of BST. Okay, so while we are going through the lecture, then you can think of other real life problem that you can solve using the BST. Different binary search tree can be represented with the same set of values. Like in tutorial 5, question number 2, we can see that there are the same sets of values, but it can represent like with different height. So the worst case running time for most search tree operation is the height of the tree. So for instance, we have this same set of value, okay, and for this a binary search tree on 6 node with height of 2. With the same set of value, we can have a less efficient BST with a height of 4. Okay, so both of these contain of the same key. So before we proceed further, I want to explain to you. We will be learning the BST insertion towards the end of this lecture, but it's important for you to know that when we do the insertion, means we are converting from array to BST. When we want to convert from array to BST, we need to follow the sequence. Okay, so let's say if 6 is appear the first one in the array, then that can be we can have like a complete 3 and even 3. So the height can be 2. It depends. Let's say the median is the first one, okay, and then after that when we want to sort the left, is like happen that the median is also the first one compared to these 2 and the other 5. So to build a BST, we cannot simply do in different order. We need to follow the order that is given. But what happened in our previous tutorial, because we just want to illustrate that BST can be in different height. Okay, so if we can look at here, right, as I said, to do the insertion or to build the BST, it needs to be in sequence, means the array, the the element sequence for this and this are different. Okay, I will repeat that later. So the basic operation for BST runtime is the order of the height. Okay, H is the height of the tree. So the height of the binary search tree can vary because of two reasons. One, because the elements keep on being inserted and deleted in our BST. So of course, if it keeps on deleting, then our height can be different. Or when we keep on inserting keys in the BST, then the height will be different. And it is also the order of elements inserted into the BST, like what I mentioned previously. So the following slide, for example, we have some order of element in an array. Okay, for example 1, if the order of elements are in increasing order, this element will be inserted into BST where it will be like a chain with a height of n minus 1. Okay, so let's say it is the array given is 1, 4, 5, 10, 6, 17 and 21. So this is how it is going to look like. Okay, so for BST, some student may answer why 5 is like right underneath the 4. Yes, you can put 5 on the right of the 4 because 5 is bigger. Okay. Alright, so if the tree is a linear change of n node, so the operation will take order of n, or is the order of the height. Okay, this one to be accurate is order of n minus 1. So this is the first example. Example that affect the height of the tree is, it happened that the order of elements are inserted where there will be a complete BST with n node. So somehow it started with 10 and then 4, so maybe then 1, or maybe it's 17. So 17 we can put at the right. So when it always, the sequence of the element always first begin with the median, okay, and then this one you can see that 4 is like the median between 1 and 5, and 17 is like the median between 16 and 21. So we will get a complete binary tree with where the operation will take order of log n or order of h. Okay, so we can see that log n and order of log n and order of n, which one is larger? Which one is larger? Choice it log n, because we have decimal. Okay, so when we look at here, this is n, and then log n should be somewhere in between here. Should be below n, and log n is higher than n. Okay, let's look at the hierarchy here. Okay, as we move up, the complexity gets higher, right? So this is n and this is log n. So to answer, log n is lower than n. So that's why here is n, here will be log n. So it will be whatever operations that needs to be done on this BST. For example, we want to search for the minimum, we want to search for the maximum. So with this, let's say we want to search the key 60. So it will be the order of log n, which is smaller than n. Question by Kishore. If the value are equal, we need to put in the left subtree or the left or the right. It can be either. Okay, I will explain to you the definition. Right after this. Okay. So for the example number 3, if the element is not in any order, so we can have we have the time complexity of log n, something like this. Okay, so maybe we have 5, 1, 4, and then 10, 16, 17, 21. So we will have this. So we can see that these 3 examples affect the height of the binary search tree. Okay, the order of elements that were inserted into the BST. So usually this one is not in any order. If we look at the common book, like the one that we are referring, the MIT book, they say it's random. But I feel that we cannot use random, because random we can still have random with some other orders. Okay, so to generalize it, we can say that it's not in any order. So we will get like this, is in between the example 1 and example 2. So let's shift to the definition of binary search tree. So this is the binary search tree property. Parent node is always greater than or equivalent to its left child node. So parent's node is always smaller or equivalent to the right child node. So to answer Kishore's question just now, the parent, so it comply. Okay, so if let's say we have here we have 5, so so it can let's say here we have 8, another 8 to be inserted, so it can be on the left or on the right, as it still comply with this. So we can see here number 5 is greater than 3 and is smaller than 7. 3 is greater than 2 and is smaller than 5. And this 7 is 8. Okay. The key in a binary search tree always stored in such a way to satisfy the binary search tree property. Let X be the node of the BST. So currently this 5 is the x. Then we can see that it still comply with the BST property. The left is smaller, which is 3, and the right is smaller, the right is bigger, which is 7. But we can see here that although 3 is smaller than 7, but we can see here that because 3 comes from the right side of the left, so this does not comply with the BST property. So 3 is supposed to be over the left side of the 5. So this is the formal definition of BST. So if y is the node in the left of the subtree of x, so this is y. Okay, so y must be smaller than the x. If y is the right subtree of x, then y must be bigger than the x. Okay, the key in the left subtree x at most. Okay, why at most? Because it can be equivalent to the parents too. So in this case, the left subtree, okay, this left can be at most 5. So is the right side. But the right side must be at least 5. Can I proceed? So that is the definition of BST. So because the right subtree needs to be at least 5, that is why this 3 does not comply with the BST property. Okay? If there's no objection, then I will continue. So how can we utilize this BST? So for today, we are going to learn about 6 different operations that can be done with BST. The first one is the tree traversal. Okay, so tree traversal is a systematic way of visiting nodes in a tree. So in here, right, we are just going to make sure that we visit all of the nodes in the tree. Given this is the BST and we want to make sure that we visit all for some reason. For the tree traversal, in this course, we are going to learn 3 ways of visiting them. Means there are 3 different sequences of visiting them. The 3 ways are the pre-order, the in-order, and the post-order. So the first one, we're going to learn about the pre-order tree traversal. This is the algorithm for the pre-order tree traversal, or they also call it a pre-order tree walk. And if you can look at this is like one of the important thing in the slide. Okay, for the pre-order traversal, it will visit the parent first, then left child, then right child. Okay, so the objective of traversal, like I said, is to make sure that we visit all. So we have 2 steps. Of course, first we need to have the BST. Then, in order to make sure that we travel with all nodes, right? Then we can do the printing. So for this class, Instead of me explaining about how is it done one by one, currently, please copy this, paste it in the chat, and please watch this. You have 3 minutes to watch it, because right now I can play using my PC, but you will not be able to listen to the sound of it. Okay, so you have around 3 minutes. I'm gonna give you 3 or 4 minutes to watch this. Please watch it now. Okay, I'll be right back at 3, 4, 3. Okay, everybody done watching? I just feel that that video give a very good way to explain, right? So that is the pre-order traversal. When they said in this video, when they said visit, means they already visit that. So we need to write it as the sequence of traveling the nodes. So it start with they visit the F, and next they visit the B, and they visit the A. Because the A has no left or the right, right? So it goes back to the B, and it will visit the D. Once they visit the D, it will visit the left first, and then it visit the right children. So that is why D, C, and E. Next, it will, because this F first visited the left, then it will visit the right. And then I, the next one is H. So this is the pre-order tree traversal. In this, we can say that it travels through this sequence. Next is the in-order tree traversal. It is also known as in-order tree walk. So this is the algorithm. In order to traverse, it takes the time of order of n. Okay, because we need to travel each of the node. So it's the same step. We need to have a BST, and then we do the printing as we travel in order traverse. Okay, so before you watch this video, I can sum up to you that the in-order travel visit the left child, then the parent, then the right child. Okay. So you're gonna paste this in our chat, and you're gonna watch it now. Alright, so I hope everybody has watched it. So we can see that it visits the left child, then the parents and the right child. So in case you got lost, here's some guidance for you. You need to print the leftmost, then print the parents, then you need to traverse through the right node. Then you need to check, does the right node has any left child? If no, then print the left. If yes, then you go back and recursively print the leftmost. Okay. So to repeat, we go to A, then B, and then equals to the right. But we visit the leftmost, C, D, then the right child. Then after that, we go to the parents. Remember, because it's left child, parents, and then right child. So since the left is done, then we do the right child. Okay, so for the right child, it doesn't have any left child, so it prints the parents first. Then go to the right, and it will visit the left child first, then only the parent. Then it will check if there's any right child that is not. So that is why it's H and I. So this is the sequence. And you can see that the example of application of in-order tree traversal is to print out all keys in a binary search tree in sorted order. This is because the BST property allows us to print out all keys in the BST in sorted order. So you can see here is A, B, C, D, E, F, G, H, and I. So you can exploit in-order traversal to do the sorting. So let's try the next example of in-order. Like the previous slide, it visits the left child, then the parents, and the right child. So let's try again. What is the order of traversal sequence? Currently, it needs to visit the left child and then visit the left child. So it's 2. Then the parent, 5. Then the right child, 5. Of course, you would check here since there's no left child and there's alright. Then it will go up to the parents, 6. Next, 7 and 8. So the order of traversal sequence is 2, 5, 5, 6, 7, 8, which is the sorted order. Okay, it's another way for you to do the sorting. Next is the third operation is the post-order tree traversal. So for the post-order tree traversal, what they do is they visit the left child, then the right child, then only the parents. So the parents will be the last one. Okay. If you want to compare between 3, right, this will be it. So this is going to be the last video that you're going to watch today. have 3 minutes to watch this video. Okay, done, everyone? All right. So this is the last tree traversal that we're going to learn in this course. Okay. So if you are interested to apply this in any problem, then you can do some research on where you can apply this, what kind of problem that you can use for this. Okay, so over here we visit the left child, then right child, then the parents. So it will visit the left child. The F will visit B. B still has left child, so it will visit the A. A is the left child. Okay, so we print A. Next, the B wants to visit the right child, but this right child has left child, so it visits the C first. Then after that, this parent visit the right child. That's why after that is E. Then only lastly is the parents. So for B is already visited the left and the right. So now it's turn to be printed. Next, this parents needs to visit the right child. So this right child this G do not have any left, so it will visit the right. When it visit the right, the I has the left child, so it will first print the H, and then the I, and then the G, and lastly the F. So this is how the post order works. So we have to do the traversal. Next is how we want to query the BST. So when we want to query means we want to search the BST. In previous lecture, we do the binary search. So binary search does not use any tree. We do the searching based on the given array, but using the binary search tree. But in here, it's no longer an array because we use the BST to represent all of our element. So let's take a look at the minimum and the maximum first. When we want to do the search, we can search the minimum by getting the leftmost of the BST. The leftmost of our BST will be the minimum number in the BST. For us to get the maximum, it will be the rightmost. We will talk about the search tree and the successor later. So this is the BST, and for the minimum key is 2 and the maximum key is 20. Okay, so this is how we're going to search. We're going to keep on searching the left child until we encounter nil. So there's no more left child. So we can return this as the minimum. On the other hand, when we want to search the maximum, we can keep on searching the rightmost child until the child has no more children. So then we have found that 20 is the maximum in this BST. So this is kind of straightforward. Next, let's talk about the tree search. Means we are not searching the minimum or the maximum. We are searching a specific key in the BST. For instance, we want to search the key 13. When we want to search the key 13, it is quite similar to the binary search that we learned before. The concept is the same. Okay, so the question here, which path to search for the key 13 in this binary search tree? This is the algorithm for search tree. So for a start, we need to see whether the key is equivalent to the X key or not. So currently, for a start, this will be our X. And this will be our key. Then we will compare. Is key equivalent to X? Is 13 equivalent to 15? No. So if no, we need to check if the key is smaller than the X. Is 13 smaller than 15? Yes. If yes, then we go left. If no, then we go right. So if yes means the key is smaller than 15, then we search left. If no, then we search at the right. So this left and right is just a layman, but in actual it calls itself, this is a recursive function, okay, where it gives the value of x left, the left of the x. So this is 15, the left of the x will be 6. So it will be sending 6 and 13 into this recursive via recursive call, and then it will do the checking. So right now, continue from here. Since 13 is smaller than 15, then we need to go left. Right? Then it calls again. Now our x is 6. Then we do the comparison. Is our key is the element that we want to search, okay? Is the key equivalent to 6? No. Then we will do the comparison. Is 13 smaller than 6? No. Okay, since no, then we need to do this else. We need to search at the right. Then it will send the x right. The x right now is 7. And the k is still remain 13. So it will call itself. Now our k, so 7 equivalents to 13? No. So we need to check if this 13 is smaller than 7. No. Okay, 13 is bigger than 7, so we need to go right. Okay, then we will be sending our x. So right now our x will be 13 and our k will be 13 too. Okay, so lastly, when it calls itself, we get that the 13 is equivalent to 13, then it will return the x. Okay, so the x is the index. It will return the x. So we can see here that we have found the key and we follow the path of 15, 6, 17 and 13. So this is how we do the search in binary search tree. I think all of you would agree that it used the same concept as the binary search as we learned before. Okay. Everyone okay?
Yes, doctor.
Okay. All right. So before we proceed further, I just want to do a revision. Okay. This revision we have learned earlier in our slide. The parent node is always greater or equals to the left child. Okay, so this is the definition of BST. So the violation of BST property, any key in the left subtree cannot be greater than the parents. So for instance, this node cannot be 6. This 6 is not supposed to be here. Okay. Although the parents is 3, but the one, this particular path is from the left side of 5. So 5 at most, whatever value at the left side of the 5, at most it will be 5. Now it's 6. So this violate the binary search tree. Another example here, same, because whatever on the right of this 5, it should be at least 5. So 4 is less than 5. So this one also violate the BST property. So this is just an revision. So this is also one of the questions in the tutorial. So this one we have discussed. And next is question number 6. But we are not going to resolve all. I can see that some of you already tried, which is good. So how we gonna answer that question? Since we are be having asynchronous learning interaction, so I emphasize a little bit more during lecture. Currently, suppose we have number between 1 to 1000 in BST and we want to search for 365. Can the following sequence of search number search 365? Can they search or not? Okay. There, if the BST property does not comply, right, then we won't be able to do the searching. So to answer this question, whether it can be searched or not, we need to have 3 steps. Okay, the first step is of course to have the binary search tree. So this is the given element. As I mentioned just now, when we want to do the insertion to a BST, it needs to follow the sequence. So we start with 2. We have 2 here. Then it followed by 252. So this 252 is supposed to be on the left or the right of 2?
Right.
To the right. Okay. Alright. 401. Left or right? 401
Right.
is bigger than 225, then it has to be on the right. 398 should be left or right? Left or right? 398 is smaller than 401, means it's supposed to be on the left. Thank you. And then we have 330. This 330 is smaller than 398. So again, it's left. 344. 344, left or right?
Right.
397.
Right.
Right. 363.
Left.
Left. Okay. So we have built our BST. Once we build our BST, we need to go to step number 2. Check if there's any violation of binary search tree property. So if there's any, how we're gonna check is, okay, for example, all the keys, okay, all the keys cannot be lesser than 2. Okay, why cannot be lesser? Because this is 2 and this is to the right side. Okay, so it needs to be at least 2. So you check, is there any 1 or not? No, right? Alright, so that's fine. Then we do the checking here to see if there's any value that smaller than 225. Then we will do the checking. This is 400 over, 300 over, all these are 300 over. So this is fine. Okay, then like this one. All left key cannot be bigger than 401 because we can see here that 401 and then left, towards the left. This one is towards the right. Towards the left, must be at most 401. So we can check that, okay, at most. So it should be okay because all of them are in 300s. Okay, so you need to check one by one on this. Okay, check one by one. I give you 2 minutes to check. And then please write at the chat whether there's any violation or not. So, any violation of BST property in this example? Rushaidi, you want to answer? No violation. Okay. Alright, so you got it right. There's no violation. So since there's no violation, then only we can do the tree search. Then we can use this algorithm. So step number 3, we use the same concept. Okay, so currently we check 365 is smaller than 2. Because right now we want to search 365 in this BST. Then we can see that, okay, 365 is bigger than 2. So we need to search at the right. Now we check 365, is it smaller than 2? No. So we continue searching to the right. Then we compare 363 is smaller than 401. Yes. Okay, if it's smaller, now we need to go to the left. So we go to the left. Then we check. Is 365 smaller than 398? Yes, it is smaller. So we go to the left. And continue. Okay. We do the checking. So now 363 is not smaller than 360, so we need to go to the right. 344. 63, it is not smaller than 344, so we still go right. Then lastly we check. Okay, since it's still not the same, the key is still not the same, then we check 363, is it smaller than 397? Yes, so we need to go left. So now X is 363. Then we found the key, because right now key equivalents to this X dot key then we return the X. Okay, so we have found this. So of course, when we look at here, we can see that, you know, the searching is the order of the height. Okay, see, we went through all of the height. But same as the binary search, right? We can do the exclusion. And when we want to search using this binary search tree, we do not need to search the array first. Remember when we wanted to do the binary search before this in an array, first we need to get it sorted first. Then, so there's like already like the time complexity involved to do the sorting. Then once we sort it, then we can exclude the half. Remember this binary search, but we were searching using an array. So we can exclude all this, and so we will just search the rightmost. So the concept is the same. But using this binary search, because this element may not be sorted, therefore we need to do the sorting first. Then, do you remember another algorithm that we have learned where we only sort the one that need to be sorted only? We don't sort all. We did not sort all. I think it was randomized select. Let us compare. When we were learning randomized select, we want to search something. For instance, here we want to search 7. Okay, so since it's like the 7th element, since the 7th element, which is 11, is around here, right? Then we ignore this. We don't even sort this. We get the pivot, and then we only sort based on the places that probably consist of the elements that we want to search. But you can see here, right, using the algorithm, the quick sort to do the sort, we still do the sorting. So although we don't sort everything like the binary search, we still need to do the sorting between the pivot. So the left should be smaller than the pivot, and the right should be bigger or equivalent to the pivot. Still some sorting need to be done. So that's so can you see right now, using BST, we can skip the searching, because the elements, the data representation that in your system is already in a form of BST. So when you want to do the searching, it will be just depending on the height. Okay, so these are the paradigms that people keep on trying to improve to reduce the time complexity. So rather than using the randomized select or binary search, you can utilize the data structure to represent your data. So for example, this BST, so that you can skip the searching, skip the sorting in order to do the search. Okay. So over here we can see that okay, we are able to search the 363. Okay, so we can try another sequence. It's also in your tutorial question. Let's try one sequence of node that could not search the number 363. Okay, for example, this C. This is the sequence. So we have 925. This 202 should be on the left, right? So the first step, of course, to build the BST. Then (911). 240 is on the left because it's smaller than 911, and then 912, 245. Correct. So we have completed the binary search tree. So currently, next step is we need to check if there's any violation of this BST property. Okay, so we can check. Okay, bye. So all left key cannot be more than 252. Okay, we do the check. So check, everything is fine. Then all right key cannot be lesser than 202. There we check. Okay. Yeah, after when we do the checking, we found out that all left key cannot be more than 911. Okay, because it is on the left. But right now we have 912. So 912 node cannot belong to the left subtree of 911. Okay, because 912 is bigger than 9 because this one 912 is bigger than 911, so it should not be on the left. So this is the disadvantage of BST, whereby it cannot, in this way then we cannot do the search. So to answer, can the following sequence search the number 363? The answer is no, we cannot do the searching for this. Okay, so this is the disadvantages. So this is the one that we have answered during lecture. Okay, this one yes, we can do the searching, and this one just recently that we did. No, we cannot do the searching. So you need to try on your own BDE whether it can be searched or not. Okay, so I'm just going to give you one clue here that one of these cannot be searched. Alright, so which one is it? You need to answer in your tutorial question, and I will mark it. Okay, please answer this question during your tutorial session. So for this Thursday, because it's public holiday, it is illegal for me to do a class. Okay, so there won't be any class, but we will declare this as asynchronous learning interaction as well. Alright, another thing to search is the successor and predecessor. Okay, so what is it? Okay, is the number comes before the number. So let's say we want before any given number. Okay, and the successor is after the number. So why do sometimes we need to use this successor? Okay, in this lecture, we will emphasize on the successor. Okay, because later when we want to do the deletion in the binary search tree, we need to find the successor in order to link back, right? I'll tell you later about that. So it is sometimes important to be able to find the successor in the sorted order to determine by the in order tree traversal. Okay, I will explain that later. So because successor is a number that comes after the given number, okay, so the successor must be bigger than the given number. In this example, the structure of BST allows us to determine the successor of the node without needing to compare the key. Okay, naively, if we want to know the successor, okay, the next bigger number in one element, if we use the array or we use like our I, we need to do the comparison of the key. But because of the property of BST, right, we do not need to do the comparison of the tree, of the key. Okay, because we already know the exact location of the BST. Okay, because they have the strict rule for them to do the sequencing of the element in the BST, so we can exploit this. So how we gonna exploit this is by using this algorithm, but I'm gonna just tell you how it works. For example, over here, we want to find the successor for 15, means the next number, the next key of 15. Instead of doing the comparison one by one, right, it is the node key 17, because since it is the minimum key in the right subtree. Okay, so for successor, of course, because it's bigger, right, bigger than the given number, so it needs to be on the right, and then it needs to be the minimum key on the right. So the minimum should be 17. So naively, we can say that yes, given all these elements, right, the successor of 15 is 17, because there's no 16 over here, right? The next number is 17. So we can, straight away find where is it. So therefore, this is the algorithm. It written exactly like how it is. So let's say this is what happened just now. On the right hand, if the right subtree node is if the right subtree node is X is empty. Okay, this one is not empty because we want to find the successor. So we need to look at the right subtree. So if it's not empty, then what we need to do is to find the minimum tree within the right, the X right. Okay, that is why this is X, and then this is the X right, which is 18. And in here, we try to find the minimum. Remember, we use this algorithm, the tree minimum. Okay, where we will return the left. Okay, it will call the tree minimum. where it will return the left. Let's say, because there are two cases. Over here, the right subtree exists. But what if the right subtree is not exist? Okay, so for example, we need to find the successor for key 13. Where is key 13? Key 13 is here. So key 13 has no right subtree. Okay, so what it needs to do is it needs to go to the here. It will be 15. So 15 will be the successor for 13. Okay, so this is the concept that the binary search tree use to find the number before and after any key. Okay. So in this insertion or in deletion, we will just give some example on how we apply the successor. Now we move to the operation to insert and delete. Okay. So I want to please keep your mind open whether you think that you can exploit this BST inside your algorithm or not. So the operation of insertion and deletion cause the binary search tree to change. Okay. So the data structure must be modified to reflect this change. Alright. So this is the algorithm to do the insertion. Okay, but for you can go through the algorithm. But for us, let's say we want to insert 13 into this binary search. Okay, so what we need to do is we will of course we need to do the comparison on the key, right, that we want to insert. Alright, but then in the end it will be inserted here. So when we use this algorithm, it will for sure comply. Hold on. Sorry about that. Okay. Where was I? So the lightly shaded node indicate the simple path from the root down to the position where the item is selected. So using that algorithm, when we do the comparison, okay, because you want to this 13, because 13 is bigger than 12. Okay, and then this 13 is smaller than then we go right. 13 is smaller than 18, so we need to move to the left. Then we need to search. This 13 is also smaller than 15. Then we go down until we couldn't find any. Okay, so when then after that we do the insertion here. So let's say, practice question number 2, we need to insert the key 16 into the binary search tree. Okay, where should we put it? Okay, we can run the algorithm. You can run the algorithm, okay, using PyCharm or something else, but conceptually, where would the 16 be? Left sub 3 of 17. Okay, left sub 3 of the 17. Okay, why? Because, okay, 16 is bigger than 12, go right. 16 is smaller than 18, go left. 16 is bigger than 15, then go right. 16 is smaller than 17, go left. Yeah, left of the 17. Okay. So that this is where we will do the insertion. So insertion can mean like the BST is already exists, or it can be like the whole thing needs to be built. Okay, so for the deletion, the time complexity is also order of height. Okay, so it when it is ordered by the height, that is why it is based on our luck when we want to do this, the order of the element being inserted. So we can have the BST like this, or like this, or like this, even giving the same set of elements. Okay, because of the sequencing. So let's take a look at, this is going to be the last algorithm to do the deletion. So for the deletion, I can sum up that there are 3 cases of deletion. One is when we want to delete the node. So it is a leaf node deletion. Leaf node deletion means there's no children at all. Or it can have 1 children, or the node itself that we want to delete can have 2 children. Sorry, this one is 1 child. Okay, 1 child, 2 children. Okay. So let's take a look at case number 1. Over here, we want to delete 4. So 4 is a leaf. So the deletion is just as simple as just delete the 4. Okay, so the result will be something like this. Oh. Okay, so now the result will be like this. 4 is deleted from the BST. Next, case number 2. 1 child node deletion. If 1 child node deletion, let's say we need to delete number 3, because this 3 is the parents of a child. So when we delete this, it's just as simple as we link up the 5 with the 2, resulting to be in this BST. So this will be the new BST. Lastly, for case number 3 of deletion, the key that we want to delete has 2 children. So delete 7, which has 2 children. So when there's 2 children, that is when we need to use the successor, as we learned before. Successor, in order successor. Okay, so what we need to do here is we need to take the successor of this 7. So 8 must be replaced the 7. 8 must be linked up with the 5 and 6. So resulting will be like this. Okay, so for the deletion, we will use the in order traversal to find the successor. So I've the last example. Okay, for the last example, just now we want to remove the 7. Now we want to remove the 3, which also a parents of 2 children. So again, we need to take the successor of 3, because after the element after 3, right, is 4. So that's why 4 is here. So when 4 is here, right, you can see that it comply with it will still comply with the BST property, because 2 is on the left of 4, which is lesser than 4. Okay, so that is all for the advanced data structure part 2. I hope all of you will find it simple to understand and be able to answer the questions. So, is it easy? Okay, I would like to explain a little bit about your final examination. Earlier, during our week 1, I did mention that the final examination will be in group. But we have changed, or I misunderstood earlier, it is an individual assignment. So each one of you needs to do it individually. Currently, we call it alternative assessment. You can call it final examination. So it needs to be submitted in week 15. Week 15. So you have the entire 1 whole week to do the alternative assessment. However, we have decided to give you more time. Okay, because in the alternative assessment, you need to read 3 different articles and do and answer questions. Okay, and then you need to implement that algorithm. When you implement in Python, you need to implement that in Python. So we have decided, instead of just giving you the entire week 15, 7 days to complete it, we are decided to give you on week 13. So you have each one of you will have 3 weeks to do your final examination. So for this final examination, there will be submission in week 15 in your spectrum. Okay, but this submission is via the Turnitin in. Therefore, everybody will need to, we will run the Turnitin in to check whether there's like similarity or not. So you have to be careful not to copy one another and not to give other friends to copy each other, to copy your work. Okay, and for the implementation, you will be given 3 algorithms. Those 3 algorithms you have learned in this throughout this course. Okay, those 3 algorithms, when you want to apply, you need to solve some problem. So you cannot be solving the same problem. Of course, if accidentally you are resolving the same problem, that is okay. Okay, but so you cannot we will check also using the Turnitin in, and we will do the comparison. Okay, so I just want to highlight to you, your final examination will be 3 weeks, 30%, and then it is an individual assignment. So currently, it might be overlapping with your group project because we try to give more time. We cannot give until week 17 because lecturers will be marking. So there will be 3 articles, 3 algorithms. So I will be marking 1 algorithm. Dr. Asmiza will be marking your second algorithm, and Dr. Raja will be marking your third algorithm. So all of us need a lot of times to do the marking because because of the due date for us to give the mark, so we cannot give until week 17. So I just telling you now so that you can plan your time. Okay, do as much as possible on the group project. Whatever questions that you have, Yap Kichin, can you write it down? Because I may not I did not jot down all of your questions just now. Is it okay? Can you write it down? Write down the questions, and then we will be giving the same written answer on your group project, right? So with that, thank you all. We have completed lecture number 8. Thank you.